So in this last video, we were talking about how dimensional analysis helps us to write any physical quantity, whether fundamental or derived, in terms of the basic 7 units, that is the unit of length, mass, time, temperature, luminous intensity, the amount of substance and electric current. So all physical quantities represented by derived units can ultimately be expressed in terms of length, mass, time, ampere, that's current, Kelvin, that's temperature, candela, that's the luminous intensity, and mole, which is the amount of a substance. How do we define these dimensions? The dimensions of a physical quantity are the powers to which the base quantities are raised to represent that quantity. Now, what are the various purposes for which we will be using the dimensional equations? One of them is to convert units of one system into units of other. We had started with this, but we have not solved the example for this yet. We did the general form. We will solve an example of this. To check the correctness of an equation, we will check that if dimensional analysis helps us to check whether an equation is correct or not, and finally to establish the relationship between various physical quantities. So let us start. Consider this equation. You have been studying this since class 10. 1/2 mv squared equal to mgh. You find this equation when you study conservation of energy, that the total kinetic energy a body possesses when it is at the lowest point in its motion is equal to the potential energy that the body possesses when it is at the highest point of its motion. Is this equation dimensionally correct? How can we check it? Well, what are the different quantities in this equation? One of them is mass. The mass gets measured by m. One of them is the acceleration due to gravity, represented by symbol g. We have the height, that's h, and we have the velocity, that's v. What are the dimensional formulas for each of this? Mass is simply m to the power 1. Gravity, acceleration due to gravity is meter per second square, so that's L t to the power minus 2. Height is simply L, and velocity is meter per second, that is L t minus 1. So for the left hand side of the equation, what is the net dimension? In the left hand side of the equation is 1/2 mv square. Half is a constant, so it has got no dimensions. For mass we have this m, and for velocity it is L t minus 1 square. So that is equal to m1 L to the power 2 t to the power minus 2. This is the dimension of the left hand side of our equation. The right hand side of our equation is mgh. M stands for this, well g, that's L t minus 2, and h is L. This is m1 L2 t to the power minus 2. So we see that the dimensions on the left hand side as well as the right hand side are equal. Whenever the dimensions on either sides of an equation are equal, we can say that the equation is dimensionally consistent. It is dimensionally consistent. Remember, when we are dealing with physical quantities, we cannot add or subtract two quantities unless they are dimensionally consistent. Like, you can add mgh with 1/2 mv squared. That's completely alright, because both of them are dimensionally equal. But you cannot add to this quantity something like momentum or something like force, because they have completely different dimensions. Obviously you can multiply or divide with them, but you cannot add or subtract quantities if they are dimensionally inconsistent. And this leads us to what is known as the principle of homogeneity of dimensions. principle of homogeneity of the dimensions. So what does the principle of the homogeneity of the dimensions say? The principle of homogeneity of dimensions says that the dimensions of all the terms on both sides of a physical equation must be the same. The dimensions of all the terms on both sides of a physical equation must be the same. So that's all about this second point, to check the correctness of an equation. Now, what about this thing, to establish the relationship among the various physical quantities? Consider this case. Suppose there is a simple pendulum. You are already aware of this idea of simple pendulum. There is a bob attached to the simple pendulum and it is oscillating to and fro about its mean position. The problem says that the time period of oscillation t, it depends on a certain number of factors. What are they? The time period depends upon the length, it depends on mass of the bob, and it depends on acceleration due to gravity. So how do we solve this kind of sums? Suppose the examiner wants us to find out that what is the formula for the time period. How will we find out? What is given is that this is how the time period depends on these three different quantities. So you assume that the time period is proportional to length to the power say x, the acceleration due to gravity to the power y, and the mass of the bob to the power z. To remove the proportionality sign, you write a constant k times L to the power x, g to the power y, m to the power z. Now here you have to assume that k is a dimensionless constant, because if k has a dimension, then this entire equation will become dimensionally inconsistent. So whenever you are assuming a constant in this kind of numerical problems, it must be dimensionless. Now what are the dimensions on the LHS and RHS? Time period means mass to the power 0, length to the power 0, time to the power 1. Dimensionless constant has got no dimension. Length has the dimension of length only. Acceleration due to gravity is meter per second square, and mass is m to the power 1 whole to the power z. Solving this gives us m to the power 0, L to the power 0, t to the power 1 equal to m to the power z, L to the power x plus y, t to the power minus 2y. And just like your childhood days, you solve the exponents, you equate dimensions on both sides. You write this by principle of homogeneity of dimensions. Z equal to 0, x plus y equal to 0, minus 2y equal to 1. I solve this equation, it gives me y equal to minus half. Substituting y equal to minus half in this equation gives me x equal to plus half, and z is already 0. So I get three values: x equal to half, y equal to minus half, z equal to 0. Now how does this equation look like? It looks something like this. The time period is equal to a constant whose value I don't yet know, length to the power half, acceleration due to gravity to the power minus half, mass to the power 0. Anything to the power 0 is 1, so this is basically k root over L by g. So we find out the time period to be some constant times root over L by g. Now since you have already studied the time period of a pendulum, you know that this constant k is 2 pi. it was known to you, but there may be cases where you don't know what the constant is. In that case, we have to perform experiments to find the value of the constant. So in this particular numerical, you can see the advantage as well as the disadvantage of dimensional analysis. The advantage is that even if we don't know how a certain factor depends on some other factors, like in this case length or acceleration due to gravity, by dimensional analysis we can find out exactly how it varies. We could even find out that it does not depend upon the mass of the ball. But the disadvantage is dimensional analysis cannot help us find out the values of the constant. For that, experimentation is necessary. So this is one of the disadvantages of dimensional analysis. This leaves us with the first idea, the first topic that we were doing, to convert from one system of units into another. So let us do a numerical which will be demonstrating this case. So this question says, it's in your book, the question number 8, it says that a body has a uniform acceleration of 45 km per minute square. This is given. They have asked us to find what would be the value in meter per second square. So I had told in that initial video that any physical quantity can be written as its magnitude times its unit in one system, which is same as its magnitude times the unit in some other system. So in this case 45, the magnitude in kilometer per minute square would be equal to some value which we will be finding out in meter per second square. So how can we write it out in the general form? We derived that n1, the first magnitude, times the dimensional formula. Now what's the dimensional formula for acceleration? It's meter per second square, and since this is one unit and this is a different unit, we use the abbreviation L1 T1, and that is equal to some magnitude n2 times a different system of units, hence L2 T2 to the power minus 2. But since acceleration has the same form of meter per second square, or length per time square, the form remains the same. We have to find out n2, so n2 is equal to n1 times L1 by L2 times T1 by T2 to the power minus 2. So this is equal to 45. L1 is our first unit, that is kilometer, 1 kilometer, and L2 is 1 meter. Time 1 is 1 minute, time 2 is 1 second to the power minus 2. So that is equal to 45. 1 kilometer is 10 to the power 3 meters divided by 1 meter. The meters cancel, and 1 minute is 60 second by 1 second. The seconds cancel. So this is 45 into 10 to the power 3 divided with 3600, which is 60 squared. Finding this out with the help of a calculator gives us the value 12.5 meter per second square. Since now you are in plus 2, you are allowed to use your calculators, but I don't know if you have them with you right now, but this is one of the numericals. There is a second numerical just following that, where they have asked us that what will be the value of a force of 100 Newton in a system having meter, kilogram and minute as the fundamental units. Meter, kilogram and minute. So let us do this sum. The given force is 100 Newton. Newton means the unit is kg meter per second square. They have asked us that what would be the value if the system of unit is kilogram, meter, but minute square. So as before, n2 is equal to n1, but what will be the units this time? Well, we have mass, length and time square, so it will be mass 1 by mass 2, length 1 by length 2 and time 1 by time 2 to the power minus 2. So that's equal to 100. The masses, well, they are kilograms in both, so 1 kg by 1 kg cancel, The length is meter in both, so 1 meter by 1 meter, they cancel. Time is what changes. From being 1 second, it has become 1 minute to the power minus 2. So this is basically 100 into 60 into 60. So that is 360000. And what would the unit of this? Well, here it was kg meter per second square, here it will be kg meter per minute square. It is very important that you mention the units properly. In the dimensional analysis, whenever you are converting from one system of units to another, you must clearly in each and every step keep a note that whether you are writing the units properly. And units, they are pretty important. Let me tell you a small story about this. It is why it is so vital that measurements be made in the right units. There was in the year 1990 a 11-year-long mission that was being carried out by NASA. The name of the mission was the Mars Climate Orbiter. You can find this in Wikipedia as well. The Mars Climate Orbiter. It was being developed by NASA at a cost of $125 million. It was supposed to study the climate, the weather in the planet Mars. But it came to a catastrophic conclusion. The mission failed. And you would be surprised to know the reason. The reason is that generally in this type of missions, different engineering teams are provided with different functions. Well, one engineering team is preparing the engine, some other team builds the propulsion system, some other builds the robotics, and so on. And all of them finally are assembled and sent to the mission. So one of the engineering team used the MKS system of units, that is the meter kilogram second, while the other team, who were the British ones, they used the FPS, the foot pound second system. As a result, in the year 1999, after 11 years of hard work, when this Mars Climate Orbiter was entering the orbit of Mars, instead of going into a stable orbit around the planet, it crashed into the planet. And all of this because of this wrong system of units used. Wrong system of units used here led to wrong calibration in the computer system and instruments. As a result, the entire mission of $125 million failed. In the next video, we shall solve some other numericals on dimensional analysis.